Good evening, everybody. Welcome to Mexborough Swinton Astronomical Society. As you will know, for the few minutes you've been sat here, we have Dr. Susan Cartwright from Sheffield University, and who's spoken to our membership on many occasions. So, Dr. Susan Cartwright graduated from Glasgow University with a Bachelor of Science in Astronomy and Natural Philosophy, physics to most people. But if natural philosophy was good enough for Newton, it's good enough for Glasgow. She then did a PhD in particle physics, also at Glasgow, and worked in Hamburg, Germany and San Francisco before arriving in Sheffield in 1989. She's currently working on neutrino oscillations with the T2K experiment in Japan, which I hope is still the case, which incidentally doesn't have any evidence that neutrinos travel faster than light, though it does have evidence that accelerators don't much like earthquakes. So can everybody put their hands up and together and welcome Dr. Susan Cartwright. Thank you.
Okay, so thank you for the invitation, and I hope that everyone can now see my screen. Shout if it hasn't come up.
It's very soon.
Good, good. So what I want to talk to you about today is the Big Bang model of cosmology, but with a focus on our observational evidence for the Big Bang. Because if you read any book on cosmology, then you'll learn all about the Big Bang, and they'll tell you about events that took place in a fraction of a second after the Big Bang, and they'll tell you about the events that took place a few minutes after the Big Bang, and they will also tell you that the Big Bang happened 13.7 billion years ago. So the question that you might ask is, how do we actually know all this? Because short of hitching a lift on the TARDIS, we obviously can't observe the origin of the universe at first hand. And since the universe is by definition the thing inside which we reside, we can't study the origin of the universe in a laboratory which is inside the universe. So the question that you would be justified in asking, indeed, as a scientist, you're obliged to ask this question, is show me the evidence. What is the evidence that allows us to develop a science of cosmology? Of course, throughout its history, humankind has developed myths of cosmology. Every religion has a creation myth, but this is very different from what we think we now have, which is a scientific picture of the origin of the universe. And I'd like to point out here that although astronomy is often said to be the oldest of the exact sciences, some parts of astronomy, and cosmology is one of these, are actually among the youngest of the exact sciences. High quality cosmological observations really only go back to the late 1950s, early 1960s. And I remember once attending a talk at the university by Malcolm Longair, who was then the Astronomer Royal for Scotland, and he said that when he started doing cosmology in the early 1960s, cosmology was a science of 2.5 facts. And so in deference to Malcolm, I think I will start by talking about the 2.5 facts that were available when when Malcolm started doing cosmology in the 1960s. And the first of these facts is that the sky is dark at night. And this may seem a statement of the utterly obvious, but in fact, it's actually an important observation, because if you think of the universe as going on forever in both space and time, that is, it's infinitely large and infinitely old, and if you think of it as not expanding, which was this was pretty much the mental model that people had from Newton to Hubble, and if you assume that galaxies are randomly distributed on a sufficiently large scale, then any line of sight in any direction should eventually hit a star. It might not hit a star for a very, very, very long distance, but it will eventually hit a star. And if the universe is infinitely old, then the light from that star has had time to reach us. If that is true, or if that were true, then that would mean that all parts of, wherever you look in any direction on the sky, you should be looking at the surface of a star. So all parts of the sky should have the same effective temperature as the average star. Now, the average star is smaller and fainter and cooler than the sun. The average star is a K or M dwarf, but they still have surface temperatures of about 3,500 Kelvin. So if this were the case, we would all be thoroughly cooked. And this is self-evidently not true. It is absolutely clear that the sky does not have a temperature of 3,500 Kelvin. And what that means is that because this follows automatically from these three initial assumptions, that the universe is infinitely large, infinitely old, and not expanding, at least one of those assumptions must be wrong. And that's why the fact that the sky is dark at night is actually telling you something. In fact, it turns out that in the Big Bang model, two of these assumptions are not right. The universe is not infinitely old, which means that light from sufficiently distant stars hasn't yet had time to reach us. And the universe is expanding, and that stretches out the wavelengths of the light from stars. So light from distant stars does not have a temperature of 3,500 Kelvin. And in fact, we need both of these things. If you read many textbooks, they'll tell you that the key point is that the universe is not infinitely old. And that's the most important thing in terms of starlight. And that's very true in terms of starlight. But as we will see shortly, there is also the cosmic microwave background to consider. And that also has an effect, when it was emitted, had an effective temperature of about 3,000 Kelvin. And the reason we are not fried by the cosmic microwave background is the expansion, which has reduced the temperature of the cosmic microwave background since its emission by about a factor of 1,000, from 3,000 Kelvin down to 3 Kelvin. And of course, at 3 Kelvin, it is not a threat, whereas at 3,000, it definitely would be. So actually, we need both of these conditions to avoid being cooked. And that brings us to fact 2, which is that indeed the assumption of a static universe is not true, that the universe is expanding. And this fact is now not quite a century old. Modern cosmology, both observational and theoretical, was born just about 100 years ago, in the period between 1915 and 1930. So any time within this decade, you could reasonably consider that you're looking at roughly the centenary of cosmology as a science. In 1915, many people know, the sorts of people who belong to astronomical societies tend to know, that Albert Einstein published his general theory of relativity. Fewer people know that Vesto Slipher published a paper on the Doppler shifts of what were then called spiral nebulae, demonstrating that these Doppler shifts were much larger than the Doppler shifts associated with stars, and also noting that most of them were redshifts. In other words, most of these spiral nebulae were apparently receding from Earth rather than moving towards Earth. A couple of years later, Einstein and also Wilhelm de Sitter published cosmological solutions of general relativity, so solutions of Einstein's field equations applying to the whole universe. In the same year, there came the first good evidence that spiral nebulae are not gas clouds in the Milky Way like other types of nebulae, but are actually external galaxies. And over the following decade, particularly the period from 1924 to 1927, first Alexander Friedmann and then Georges Lemaitre independently produced the modern cosmological solution of general relativity, the so-called Friedmann-Lemaitre equation. And Edwin Hubble produced clearer and indisputable evidence that spiral nebulae were indeed external galaxies. And over the period 1929 to 1931, Hubble went on to show that the Doppler shifts, the red shifts of spiral galaxies, were proportional to their distance from us, and this demonstrates that the universe is indeed apparently expanding. So this is Hubble's diagram from 1929, and it is, like most early observations, not the world's most convincing plot ever. I should say that the 1931 paper is much more convincing. You certainly can see that the top left corner and the bottom right-hand corner of this diagram are pretty empty, and therefore it does appear to be true that the recession velocity as calculated from the redshift of the galaxies does increase with distance. You could certainly fit other curves besides a straight line to these very scattered data. The advantage of fitting a straight line, first, is that it's the simplest thing you can fit. And secondly, that if the relationship between distance and velocity is linear, then it doesn't matter where you are. Somebody in a galaxy a long time ago in a galaxy far, far away would observe exactly the same linear relationship between distance and velocity as we do here. And that wouldn't be true if this were, if velocity were proportional to distance squared or square root of distance or anything like that. It is specifically the case for a relationship that is a straight line. Now, nowadays, we can certainly demonstrate with great precision the relationship between redshift and distance. This is relatively recent data from Adam Rees using type 1a supernovae. And you can see that this is really a very nice relationship. There is no doubt that these data fit the line that has been drawn through them. There is no a huge scatter as there is in this case. In fact, the theories that were the solutions to Einstein's field equations that were developed by Friedmann and Lemaitre show that what we call the Hubble constant is not actually constant over the history of the universe, and cosmologists tend to call it the Hubble parameter rather than the Hubble constant to account for this. And that's why in the x-axis of this modern plot, you don't simply have redshift, you have some fiendishly complicated thing, and that's actually correcting for the change in the value of the Hubble parameter over very long distances, because these data points, as I said, are type 1a supernovae, and the advantage of type 1a supernovae is that they are visible out to extremely great distances, and at those extremely great distances, one really does have to take account of the fact that the Hubble parameter, the value of the Hubble parameter 5 billion years ago, is not the same as the value of the Hubble parameter today. The natural deduction from the fact that the universe is expanding is that the galaxies that we now see at great distances used to be closer together. And with a linear expansion, since the galaxies twice as far away are moving twice as fast, if you run time backwards, they all wind up in the same place at some point a well-defined time ago. And as I said, if you have a linear expansion like this, it looks the same from any vantage point. So you can't say that they would all collapse on top of us. They would simply all be in the same place at this time, which corresponds to the beginning of the universe. Now, Hubble himself never actually accepted that literal interpretation of his law. And part of the reason for that is that Hubble's original value of his own constant was very much too large. If I go back to the last plot, you will see that Adam Ries's paper, the value of H naught is 73 kilometers per second per megaparsec. Here we have 2 megaparsecs, and that 2 megaparsecs corresponds to about 1,000 kilometers per second. So Hubble's value of the Hubble constant was about 500 kilometers per second per megaparsec, which is rather different from 73. And if you run time backwards with H naught equal to 500 kilometers per second per megaparsec, you come to the conclusion that the Big Bang happened somewhere around 1 to 1.5 billion years ago. And in 1929, this was somewhat embarrassing because particle physicists using radioactive dating of rocks, in particular a chap called Arthur Holmes, had managed to demonstrate that the rocks of the Earth, the oldest rocks of the Earth's crust, were about 3 billion years old. So we deduce from this that the Earth is twice as old as the universe. And this is not a happy deduction. And therefore, this makes a literal interpretation of Hubble's law look rather shaky. And indeed, that was one reason cited by Fred Hoyle in the 1940s for the introduction of the steady state model of the universe, where the universe expands, but new matter is created so that the density of the universe always remains the same, even though it is constantly expanding. And obviously, under those circumstances, the universe can be infinitely old, and its age is not in any way related to the actual value of H naught. So, as I say, that was one reason. The inconsistency of the inferred age of the universe and the age of the Earth was one reason that Hoyle cited for wanting to introduce this model. And this problem was only fixed in 1958 by Alan Sandage, who found two errors in Hubble's distance ladder, which had caused him to severely underestimate the distances of the galaxies he was observing. I should here insert a shout out to the Dutch astronomer Jan Oort, who was, as far as I can tell from the literature, the only person who said, when Hubble originally published his estimate of the Hubble constant, that Hubble's value was wrong, and that Hubble's statement that the uncertainty on that value was only about 10% was also wrong. Oort said quite correctly that the value must be smaller than Hubble thought it was, and that the uncertainty on the value was very large. But nobody seems to have listened to him. I have great respect for Jan Oort, because he was also the only professional astronomer in the 1930s who took the early beginnings of radio astronomy seriously. He seems to have had very good instincts for what was important. Anyway, those were our first two facts. Malcolm Longyear's fact 2.5 is that the universe is evolving with time. And in the early 1960s, this was only half a fact, because there was some evidence, but not enough to prove the case beyond reasonable doubt. I think you would probably have won a civil court case. It was probably proved on the balance of probabilities, but not beyond reasonable doubt. So the way we understand that, or can discover that the universe changes with time, is because the speed of light is finite. And therefore, any object that is at a large distance from us is being seen as it was a very long time ago, because the light from that object has taken a long time to reach us. For example, if you look up at the Andromeda galaxy, that's about 2 million light years away. So the light that you are seeing left the Andromeda galaxy 2 million years ago, when there were upright apes walking the plains of Africa, occasionally chipping out stone tools. And the Andromeda galaxy, as you know, is one of the closest galaxies. So objects at very large redshifts are being seen as they were billions of years ago, and they're therefore being seen when they were billions of years younger. And if we find that the properties of astrophysical objects change as a function of redshift, that is to say, as a function of distance, that implies, therefore, that they are changing as a function of time. And that strongly suggests that the universe is of finite age, because if the universe were infinitely old, you would expect the populations of objects in it to have reached a sort of steady state where nothing much changes. And nowadays, it is very, very clear that, that this is true. Things have obviously moved on in the past half a century. So, for example, here is a plot by Maddow and Dickinson from about 8 years ago, showing the average star formation rate in solar masses per year per cubic megaparsec as a function of the so-called look-back time, which is to say the time it has taken the light to reach us. So what you see is that there was not much star formation going on in the very early universe. Then star formation ramped up. It reached a peak about 10 billion years ago, which is around the time that the oldest star, that the globular clusters in our galaxy formed, and the oldest stars in the disk. And it has been declining since then as the gas from which stars are formed is used up. Our own solar system formed about 4.5 billion years ago, so about here. And similarly, we see that if we look at the number of active galactic nuclei, quasars and radio galaxies, then we also see that this number reaches a peak, actually at a not dissimilar time, around a redshift of 1.5 or so. So that would correspond to a look back time of about 9 billion years. And so it is now a well-established fact that the universe is evolving with time, and by implication that the age of the universe is not infinite. And that allows us to talk about the conditions in the early universe. And we see evidence that the early universe was very different from the universe we see today, and in particular, the early universe was hot. And the first evidence of this is that most elements are made in stars. So, for example, the oxygen that you are currently breathing was produced by the explosion of a massive star in a core collapse supernova. And the iron in your blood that allows you to breathe that oxygen was probably produced in a type 1a supernova, an exploding white dwarf. And the nitrogen that makes up most of the Earth's atmosphere and the carbon that is the basis for organic molecules were produced in stars quite similar to the sun in a more evolved state. However, there are some exceptions to this. In particular, the isotopes between hydrogen and carbon, particularly the heavy isotope of helium, of hydrogen, hydrogen 2 or deuterium, the 2 stable isotopes of lithium, the single stable isotope of beryllium, and the 2 stable isotopes of boron are actually destroyed in stars. All of these isotopes are less tightly bound than helium-4, which is an exceptionally tightly bound state for a light isotope. And so all of those nuclei harbor a secret ambition to become helium-4. And in the conditions in the cores of stars, they realize that ambition. And deuterium combines with other protons and deuterium nuclei to become helium-4. And lithium, beryllium, and boron all get split in 2 to become 2 helium-4s. And also, there is lots of helium-4 about. There is much more helium-4 than you would expect if you were only looking at helium-4 made in stars. Now, some of these isotopes, beryllium and boron in particular, seem to be produced by cosmic rays. You start with carbon, you accelerate carbon to very high energies, carbon collides with innocent intergalactic gas, and bits get knocked off. But this doesn't account for the abundance that we see of deuterium, helium-4, and perhaps lithium-7. And these seem to be made in nuclear reactions shortly after the Big Bang, when the universe was extremely hot. And indeed, early in the history of the Big Bang theory, the theoretical nuclear physicist George Gamow tried to explain the formation of all the elements by nuclear physics in the early universe, but that doesn't work because of the extreme stability of helium-4, which means that there is no stable nucleus of mass 5 because they all decay instantly to helium-4, and there is no stable isotope of mass 8 because they all break apart instantly into 2 helium-4s. So you can't build up to heavier elements in the early universe. But you can make light elements. And here is a plot of how the abundance of different elements evolves in the first few minutes after the Big Bang. This is a logarithmic scale, so this is 1 second after the Big Bang. Sorry, this is 10 seconds after the Big Bang. This is 100, This is 1,000, so 3 hours. And this is 10,000. That's 10,000 is 3 hours. That's about 20 minutes. And what you see is that you start off with just protons and neutrons. Most of the protons stay put, but the neutrons combine with protons, and most of them wind up in helium-4. There's a little bit of deuterium that survives. There's a little bit of helium-3. The neutrons themselves and hydrogen-3 and beryllium-7 are all unstable. The neutrons will decay to protons, a hydrogen-3 will decay to helium-3, and the beryllium-7 will decay to lithium-7. So what you're left with is hydrogen, helium-4, deuterium, helium-3, and lithium-7. And you can figure out how much of each of these you expect to get. And this is the lines on this plot. You can compare that with the observed abundances, which are the yellow boxes. The size of the box represents the experimental error. And the most sensitive measurement that we have turns out to be the deuterium abundance. And what this calculation depends on is the lifetime of the free neutron, which we can measure in the laboratory, the number of species of neutrinos, which we know, and the rate of expansion of the universe, which we can measure, and the density of ordinary matter in the universe. And so that is what's being plotted on the x-axis of this plot. And what you see is that our very accurate measurement of the deuterium abundance in the early universe allows us to define this pink hatched box here, which is the best fit to the implied density of ordinary atoms in the universe. And the interesting thing about this plot is that that pink hatched box corresponds pretty much exactly to the light blue underneath it, which is the estimate of the same quantity from the cosmic microwave background, which we'll come to in a few minutes. And notice that these agree very well. And this is further evidence of the correctness of the model that we are using, because we've used two completely different measurements to deduce a value for this parameter, the density of ordinary matter, and we've got results that agree with each other perfectly. And if this agreement were accidental, it's very unlikely that two totally different measurements would yield the same result. So, what did that light blue box come from? Well, the most convincing evidence that the universe is evolving with time is the cosmic microwave background. If we assume that the universe starts in a hot, dense state, which is what you would expect if you took all the galaxies that we now see and squashed them into the same place, you would expect the result to be very dense and very hot. Then you would expect that it would be completely ionized into individual electrons and protons, because it would be very hot, and it would also be very dense. And that makes it opaque to radiation, because photons interact very readily with charged particles. So in a situation where you have the universe being a dense plasma of ionized of charged particles, photons would not travel very far. And it turns out that a hot, dense material is what you need to produce what we call a black body spectrum. The black body spectrum is a spectrum that assumes that the photon energies have been completely randomized by collisions with other particles, and the energy spectrum of such photons depends only on the temperature and not on the nature of the object. This plot shows the black body spectrum for typical stellar temperatures. You can see that the hotter temperature is, the more photons are emitted, and the shorter is their typical wavelength. Now, as the universe expands, the wavelength stretches, the number of photons per cubic meter decreases because the volume is increasing, and therefore the apparent temperature of your radiation will shift downwards. And at some point, you reach the point at which protons and electrons, which up until now have been living completely independent lives, find it energetically favorable to combine to produce neutral hydrogen. This is somewhat unrealistically typically referred to as the epoch of recombination. Recombination isn't a very good word because it implies that this is not the first time the protons and electrons have been combined, and in fact it is. It should really be called the epoch of combination, but recombination is the standard spectroscopist's word for protons and electrons coming together to make neutral hydrogen. Now, the key point about neutral hydrogen is that word neutral. Hydrogen atoms do not have a net electric charge because there's one electron and one proton. And photons are much less interested in neutral objects than they are in charged objects. And so once the universe becomes neutral, it also becomes transparent. And since that time, the photons have no longer been interacting very much with the rest of the universe. To use the jargon, they are decoupled. And so their spectrum has remained pretty much as it was, except for being stretched by the expansion of the universe. So, as I said earlier, it started out at a temperature of about 3000 Kelvin, and it's now at about 2.7 Kelvin. So, so this is a prediction of the Big Bang model of the universe. And in fact, that prediction was made very early in the history of the Big Bang theory in about 1950 by Alpha and Herman, and was promptly forgotten, probably because in 1950 there was no obvious way to observe such a microwave background, and so people looked at the prediction and said, well, that's pretty useless, and promptly forgot about it. And so it was famously, in fact, discovered in 1965 by Penzias and Wilson, who got the Nobel Prize for it, which I always thought was very unfair to the cosmology group at Princeton, who had independently rediscovered this prediction and were building a microwave antenna to look for it. So if it hadn't been discovered accidentally by Penzias and Wilson, it would have been discovered on purpose by Roland Wilkinson only about 6 months later. And since then, the cosmic microwave background has been measured many times from the ground at long wavelengths, from balloon observations at slightly higher wavelengths, and from satellites at shorter wavelengths. And you can see that all of these data fit remarkably well to a black body spectrum at 2.725 Kelvin. And in fact, the black body spectrum that was produced by the Cosmic Background Explorer COBE satellite back in the 1990s was so precise that the limit on trying to measure deviations from a perfect black body was set by the fact that they didn't have as perfect a laboratory black body to calibrate on. There was no measurable deviation at all from the theoretical prediction. And this is essentially proof that the early universe was hot, dense, and opaque. Because to produce such a perfect black body spectrum, the universe must have been opaque to radiation, because that's the conditions in which you get this spectrum. at just one point in its past, in order that that spectrum has a single unique temperature. If you make black body radiation continuously over a period of time, you will get different temperatures now, because black body spectrum from different times in the past will have been redshifted to a different extent, and adding up lots of black body spectra at different temperatures does not produce the same thing as a black body spectrum at a single temperature. So this spectrum is totally natural in the Big Bang model. It's extremely hard to avoid having a cosmic microwave background if the early universe was hot, dense, and opaque. But it's very difficult to get this kind of behavior in any other model. And in fact, this long wavelength part of the spectrum was measured mostly by the Princeton group in the late 1960s. And that was what basically killed off the steady state model of the universe. It was just impossible to account for this black body spectrum. However, although the cosmic microwave background in its broad aspects is strong evidence in favor of the Big Bang model, when you look at it in more detail, it seems to be rather too good to be true. And the problem is that although we typically look at these maps that are produced by spacecraft like WMAP and Planck, and it looks as though the cosmic microwave background is patchy, you have to remember that this is a very exaggerated scale. In fact, the most noticeable feature of the temperature of the black bodies of the microwave black body spectrum across the sky is how constant it is. These variations between hot spots and cold spots are variations of only a few parts in 100,000. And this is hard to understand because if you think about it, this radiation has been traveling unimpeded since about 400,000 years after the Big Bang. So if I look north, that radiation started out 400,000 years after the Big Bang, has traveled for 13.7 billion years, and has just entered my microwave receiver. And if I look south, the same is true. So it seems clear that since photons from north and south are only entering my microwave receiver now, they can't possibly have reached, the photons from the south can't possibly have reached the north, and photons from the north can't possibly have reached the south. And in fact, it turns out when you look at the mathematics, it's actually worse than that. Regions more than about 1 degree apart can't have talked to each other before the cosmic microwave background was emitted. So if they haven't exchanged photons, how do they know each other's temperature well enough to be equal to 1 part in 100,000? You could understand that they'd all be roughly the same temperature, but not that precisely. You might expect that some bits of the sky would be at 1 Kelvin and some would be at 2 and some would be at 3, but they're not. They're all at 2.725. And this issue was solved about 40 years ago by Alan Guth and independently by Andre Linde. And both of them came up with the suggestion that is now known as inflation. And the idea is that for a very brief period, very soon after the Big Bang, and I mean about 10 to the minus 35 seconds after the Big Bang, so that's 0.3401 second after the Big Bang, the universe went through a brief period, a tiny fraction of a second, where it expanded very much faster than you expect in the standard Big Bang theory. And in fact, it expands very much faster than light during this very brief period. Hang on, I hear you say. Relativity says that nothing can travel faster than the speed of light. And this is true if you are talking about objects traveling through space, such as galaxies, meteors, and spacecraft. But general relativity does not preclude the universe space-time itself expanding faster than the speed of light. Space-time can expand as fast as it pleases. And this very brief period of extremely rapid expansion also allows the cosmic microwave background to be almost but not quite uniform. And that is, that's a subtle point, but it's important, because you could argue that the reason that the cosmic microwave background temperature is uniform is that it has to do with conditions actually at the Big Bang that forced it to be uniform, in which case you turn the question inside out and say, well, why isn't it precisely uniform? But in inflation, you get it almost completely uniform, but you expect tiny variations, and the spectrum of those tiny variations that you expect agrees with what we observe. It also makes the geometry of the universe flat, and this is also consistent with observation. So here are a couple of diagrams trying to show what happens. So this is a plot showing the radius of what is now the observable universe. And so before inflation, the observable universe, what is now the observable universe, has a radius of about 10 to the minus 53 centimeters, and that is at 10 to the minus 45 seconds after the Big Bang. And that is such a small distance that photons could have traveled through that extremely tiny distance many times. And therefore, it makes sense that that very tiny region of the universe is all at the same temperature. Then inflation happens, and it suddenly expands by a factor of about 10 to the, in this particular model, about 10 to the 55 or so. And then inflation stops, and you get the expansion, the slower than light, steady expansion that we see today. And the key point here is that because this very tiny pre-inflation region was all at the same temperature, this much larger region is still all at the same temperature. And this is a more schematic diagram of the same sort of thing. And it is very difficult to find evidence for the existence of inflation. But one of the things you could look for is that we expect that the inflation period should generate gravitational waves. And although these will be much too feeble to be detected by experiments like LIGO, they would leave characteristic polarization signals in the cosmic microwave background, which we can try to look for. And they haven't been seen so far. There was a false alarm a few years ago, but were they to be observed, then that would provide us with direct observational evidence for inflation. So the hot Big Bang model was established as our best model of the universe with the discovery of the black-body spectrum of the cosmic microwave background in the late 1960s. And it remained a happy little model until the late 1990s. And before 1980 or so, there was this slightly niggling worry of why is the cosmic microwave background so uniform? But if we bolt inflation onto the very beginning of the Big Bang, then that problem is solved. So it seemed around about 1990 or so, as though we had a pretty satisfactory model of the universe. And according to that model, we expected that the expansion rate of the universe would be slowing down over time because of gravity. And that slowing down would depend on the density of the universe. And this is an interesting parameter, and therefore people set out to try to measure it. And in order to measure it, you need to be able to measure distances out to redshifts of order 1. And the only realistic way to do that was using exploding white dwarf supernovae. And two teams, the HiZ Supernova Search and the Supernova Cosmology Project, set out to do this, and they both reported in 1998 or so. And what they found, to everybody's great surprise, was that the expansion was not, in fact, slowing down, it was speeding up. And you can see this in this early plot, 2003, the points at high redshift, this dotted line is what they expected to see, expansion slowing down, and all the points at high redshift are above that line. And indeed, they're even above this line, which was the sort of the least matter they thought they could get away with. And this is consistent with a universe where the expansion is speeding up. And this came as a bit of a shock. I remember when it came out, I was actually working at MIT, and I said to Alan Guth, yes, Mr. Inflation, what do you think of these supernova results then? And Alan said, I hope they're wrong, because it was just very, very difficult to understand what was going on. And in order to explain acceleration of the expansion, we had to reintroduce the cosmological constant, which was originally, ironically, introduced by Einstein in order to develop a model that didn't expand at all. He sort of balanced the gravitational effect of matter with the inflationary effect of the cosmological constant to get a universe that was static, which he thought was consistent with the data that was available in 1917. And when Hubble demonstrated that the universe is not static, that it's expanding, Einstein apparently commented that the introduction of the cosmological constant was probably his greatest blunder. This shows that the blunders of genius are not to be taken too lightly, because in fact, having spent the times between about 1929 and 1999 happily setting the cosmological constant to 0, these data made us bring it back. And you can see here that this model that fits the data well has a cosmological constant, which is usually designated by lambda. That upside down V is the Greek capital lambda, of about 70% of the energy density of the whole universe is cosmological constant, and about 30% is matter. And this was, as I say, a very early analysis, but that 30% matter, 70% cosmological constant has remained pretty much the benchmark model ever since. And here we see some more recent data, and these data show that the universe is accelerating, expansion is accelerating now, but in the past it was actually decelerating as expected without the cosmological constant. And that is what we would expect, because according to the Friedmann-Lemaitre model of the Big Bang, the cosmological constant is less important in the past. It becomes progressively more important as time goes on. And it was also consistent with data from other observations. This orange here is from an early analysis of the spectrum of the cosmic microwave background. This green splodge here is from analysis of large-scale galaxy redshift surveys, and they all coincide in this little purple ellipse here, which still corresponds to about omega lambda equals 0.7, omega matter equals 0.3. And one of those pieces of data, this orange thing, is labeled CMB. And what that comes from is analyzing those tiny temperature fluctuations. They don't seem very significant, 1 part in 100,000. In inflation, they are explained as being caused by quantum fluctuations due to the uncertainty principle, which, because the inflation expands the universe by such an enormous factor, those tiny quantum fluctuations become blown up to macroscopic size, and they leave an imprint on the cosmic microwave background. Now, the actual locations of the hot and cold spots are just random. They're just if you were to rerun the Big Bang from the beginning, they'd come out in different places. But the characteristic size of those variations, both in terms of how much hotter or colder than the average they are, and also how many degrees they subtend on the sky, those depend on many important cosmological parameters. They depend on the Hubble constant, they depend on the density of matter in the universe, they depend on the nature of the dark matter. And analyzing these features has yielded a wealth of high precision cosmological data. And so it's these observations of the cosmic microwave background that have really made the 21st century the era of precision cosmology. And to give you a feeling for how this works, what you do is you analyze those spots so that you get what's called a power spectrum, which essentially is telling you about the characteristic size of the hot and cold spots in the cosmic microwave background. And this little animation by a Chicago cosmologist called Wayne Hu sort of shows, as you track through this power spectrum, the corresponding size of the hot and cold spots. So small values of this parameter L, you're looking at big patches, and at large values, you're looking at small patches. And you can see from the data that they prefer an angular size of about 1 degree, and then there are higher harmonics of this, just as if you pluck a guitar string, you get higher harmonics of the fundamental note. And the heights and positions of these peaks encode information about the properties of our universe. And the green line here is a fit to these data, and you can see that our hot Big Bang model produces a really very good description of these points. So to give you a feeling for how this pattern would change if you changed cosmological parameters, here are some more of Wayne Hu's animations. This shows the effect of changing the value of the total energy density of the universe with or without a cosmological constant. And you can see that if you change the density of the universe, the position of the peak changes. The heights of the peaks don't change very much, but their positions change. If you increase the density of dark matter in the universe, dark matter tends to damp down the peaks, so the peaks stay in more or less the same place, but their heights change. And if you change the amount of ordinary atomic matter, this again affects the heights of the peaks, but it affects it in a different way. It tends to change the even-numbered peaks with respect to the odd-numbered peaks. So you can use the observed spectrum to obtain values for these parameters separately because they affect the spectrum in different ways. And if we combine our cosmic microwave background data with evidence from the more recent universe, such as galaxy redshift surveys, we can get a benchmark model of cosmology. And here it is. You have about 70% of the universe is, of the energy density of the universe is made up by the cosmological constant. About a quarter is made up of dark matter, and the remaining 5% or so is made up of normal atomic matter, such as you and me. And so if we look at a paper by the Planck collaboration, for example, they quote the Hubble constant as 67.4 plus or minus 0.5, the density of ordinary matter as 0.315 plus or minus 0.007, and the density, sorry, that's the density of dark matter, and the density of ordinary matter as 0.0493 plus or minus 0.00034. And you can see that these numbers are all precise to about 1% in these two cases and about 2% in this one. And this is really a remarkable achievement. We tend to lose sight of this because it's become a sort of commonplace of cosmology now. But 30 years ago, these numbers had uncertainties that were a factor of 2, and now they're 2%. So this is a testament to just how much observational cosmology has changed over my professional career. So you might be forgiven for believing that we now understand the universe. I regret to report that this is not true. Or perhaps I should say I'm pleased to report that this is not true, because if it were true, cosmologists would be out of a job. We have a good idea of the properties of dark matter, and we have a good idea of how much dark matter there is, but we have no idea what it actually is. And that's why people like Ed Dorr and Vitaly Kudryavtsev are in this department are searching for dark matter to try to identify it and answer this question. We have absolutely no idea what drives the cosmological constant. In Einstein's original model, the cosmological constant behaves like an energy of empty space, a vacuum energy. Many particle theorists look at more general models of this, and therefore it now tends to be called dark energy rather than the cosmological constant, because in many more complicated models it's not actually constant. But there is no good model for this stuff. I have no idea what it is, and neither does anybody else, even if they say they do. And also, we are now finding, now that we are looking at 1% precision, we are finding that these high precision results from different methods don't agree as well as they appeared to when the error bars were a bit bigger. Most noticeably, there's a strong tendency for traditional measurements of the Hubble constant using direct measurement of the expansion to differ from the measurements inferred from the cosmic microwave background. So here is a plot that I took from a recent review article, and the values from the early universe, from the cosmic microwave background, combined with galaxy surveys and various other things, tend to give you values in the high 60s. This one is 67.4 plus minus 1.2, whereas values using measurements using redshift versus distance plots tend to give you values in the low 70s. So these differ by about 6, and both of them have errors of roughly of order 2. And if you combine these different traditional measurements, you find that because the combination reduces the uncertainty, when you compare with the early measurements, you get disagreements of the order of 5 error bars. And that is very, 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 very unlikely to occur by chance. And you might argue that, yeah, we've been here before. Remember that Hubble thought his value of 500 kilometers per second per megaparsec was accurate to probably within plus or minus 10%, and certainly within plus or minus 20%. And it was actually out by a factor of 7. So clearly astronomers can't calculate their systematic error bars. And that's what I thought when it first appeared. But this discrepancy has now actually persisted for about 10 years, and it's found in multiple analyses. So it's not just one analysis that's getting an anomalous result. And here you can see that the authors of this paper use different methods of calibrating the redshift to distance relationship using Cepheid variables, the traditional method as pioneered by Hubble, using the tip of the red giant branch, or using Myra variables. And they do change a bit, but not by very much, and certainly not by enough to bring them into agreement with the cosmic microwave background measurements. So this could be the first evidence for more complicated cosmology, because these measurements all assume a cosmology in which the dark energy is in fact a standard cosmological constant a la Einstein. Maybe that's wrong and it should be more complicated, and perhaps that would allow us to bring these measurements closer together. So to summarize, I hope that I have convinced you that when you read cosmology books and they tell you what happened in the first few seconds after the Big Bang, they are not making it up. There is good observational evidence for the features of the Big Bang as they are described in your textbooks. I haven't talked very much about alternative models, basically because they don't work. Either they don't fit at all, or if you can force them into working, you wind up with something that is practically impossible to tell from the standard model. For example, there are some alternative models involving extra dimensions, which can mimic the standard cosmological model very closely. So although they're conceptually different, they have very similar predictions. I hope I've also shown you that observational cosmology is no longer, as it was 60 years ago, a science of 2.5 facts. It's become much more powerful and much more precise, and therefore a much better test of our theoretical understanding. And this is beginning, as we saw in the last couple of slides, to throw up some possible difficulties for our standard model. And even if these do turn out to be a case of underestimate of systematic errors rather than a real difference, there's still a huge amount that we don't understand, such as the nature of dark matter and even more the nature of dark energy. But our measurements are improving all the time, and we can hope that some of these more precise measurements will lead to a better theoretical understanding, while still recognizing that the basic framework of our cosmological theory is completely underpinned by observational data, and it's not going to go away. Okay, so that's it. Thanks very much. And I will stop sharing now so I can see you again, so that you can ask any questions that you might have.
So, thank you very much. Once again, an absolutely thought-provoking talk, and I'm so pleased that there's still a lot for you to do and that you will be gainfully employed for many years to come. So, ladies and gentlemen.
Well, I won't be gainfully employed for all that many years to come, because I shall be reaching retirement age in not all that many years.
Well, as long as you want to carry on doing it, then let's put it like that. So, ladies and gentlemen, as usual, a digital hand if you have a question for Sue, please, so that we can bring people in, and I'll try and keep control of people down in the club room. We've got Mick here in the club room who's going to ask a question. You want to kick off, Mick?
Yeah, sure. Going back to inflation, if space-time is expanding greater than the speed of light, anything within that space-time, how is that not relatively travelling faster than light?
They are, but they are at rest with respect to their local coordinate system. So it's like the difference between walking along the bridge from Manchester Airport railway station to the airport versus taking the rolling walkway. If you are lazy and take the rolling walkway, then you are moving with respect to the viewer from outside, if you like, but you yourself are stationary in the coordinate system of the rolling walkway. And in the same way, two galaxies during inflation, or two bits of hot dense material during inflation, would each see themselves as being stationary, even though the distance between them is increasing at faster than the speed of light. And that's what makes the difference from the point of view of general relativity.
Okay, Mick. I think he's going to have to think about that one.
Yeah.
Mick Nichols. Mick, can you unmute yourself, please?
I do apologise. I've had to come on my phone, so I'm messing with a few buttons. You mentioned about expansion and galaxies moving away from each other. That bit I understand, but if they're moving away from each other, what makes them collide?
That's because if you have two objects that are gravitationally bound, they sort of fall out of the overall expansion. So, for example, our solar system is not expanding because it's a bound system, and the Milky Way and the Andromeda Galaxy, the local group of galaxies, are a gravitationally bound system, and that is also not expanding. And in fact, the Andromeda Galaxy is coming towards us and will collide with the Milky Way in about 3 billion years or so. So if you have gravitationally bound systems, they're not within what's called the Hubble flow of overall expansion. If you think of this in this sort of general relativity picture of the curvature of space-time, you can think of bound systems as being little sort of upside-down mountain peaks, if you like, in the general smooth flow, and they stay the same size.
Thank you.
Okay, Mick. Peter Lloyd, Doncaster Astronomical Society. Peter.
Thank you, Paul, and thank you, Susan. Most enlightening talk. Simple question, I hope. If you use, for example, a 1A supernova to measure distance and rate of recession, do you get those distances and rate of recession as they are now, or as they were when the light left them?
That's an interesting question. Distances in that kind of distance is actually quite complicated to define. And there are different measures of distance. And for nearby objects, they're equivalent. But as you get further away, they actually differ. And the kind of distance that you measure with type 1a supernovae is called the luminosity distance, because you're measuring the brightness and comparing it to the brightness that you know supernova, type 1a supernovae have. And the luminosity distance is the distance as it is now. Whereas there are other measures of distance that measure what's called the angular diameter distance. And the angular diameter distance is a measurement of the distance as it was when the light was emitted. So the concept of distance has to be defined extremely carefully when you're working at these very large distances.
And doesn't that therefore affect the Hubble constant as to what value you get? Because it all depends
it absolutely would. But of course, cosmologists know what kind of distance they are using, and they correct for it. And the Hubble constant is traditionally measured in terms of luminosity distance. So if your distance indicator is an angular diameter distance, you correct for that before you measure your Hubble constant.
But you say that the luminosity distance is the distance it is now, rather than the distance it was when the thing exploded.
Yes.
I'm tempted to say why, but perhaps I don't.
It's because as your light travels between the distant supernova and us, it is affected by the expansion of the universe, and therefore the rate at which your photons arrive at the receiver is less than the rate at which they left the supernova, because the space between them has been stretched, and therefore the distance that you measure is larger than it was when the light left the supernova.
Yeah, that's the redshift, isn't it? Yeah,
that's the redshift. Yeah.
I will have to think about that one. Thank you.
Okay, Peter. Andy Deavy.
Hi, Sue. Fantastic talk as usual. Really enjoyed it. My question is, has there been any either theoretical modelling as to what actually propagates inflation?
Yes. Yeah, there are theoretical models for it. It's one of these cases where it's very difficult to explain without going into the mathematics of it. But basically, inflation, the mechanism for inflation is very similar to the Higgs mechanism. It's a so-called scalar field, and you can show in quantum field theory that introducing such a scalar field can drive inflation. Basically, what you have is what's commonly called a wine bottle potential. If you think of the base of a red wine bottle that has this sort of peak in the middle, this is a situation in which your field starts off in the middle of the wine bottle, and that is a state of unstable equilibrium. It's like trying to balance a pencil on its point, and there's a lot of stored energy in this field, and when it falls off towards the minimum, which is around the sides of the wine bottle, you release that energy into the universe, and that's what drives the rapid expansion. And one of the weak points of inflation is that you have to tune this inflation potential quite carefully to make it behave as you want it to. And many theoreticians regard this as rather unnatural, and they prefer something that was cleaner. On the other hand, the Higgs boson really does exist. So in at least one case, positing a scalar field to explain a phenomenon we didn't understand turned out to be right. So the fact that it seems to be the first, as I will say as an experimentalist, it seems to be the first weird thing that theorists reach for in their toolkit when they have something that they don't understand, doesn't necessarily mean it's wrong, because in the case of the Higgs mechanism, it was right.
Can I just say that from what I've read, the only proposed object that harbours sufficient energy that could propagate the Big Bang is some sort of black hole that we know of at the moment. So if there was some method of exploding a black hole, to me, surely that would instantly inflate once the gravity were broken to the event horizon or even beyond. So that will give a very easy mechanism to achieve inflation.
The difficulty with inflation isn't achieving it. There are various ways of doing that. It's making sure that you can fall out of it. That was the problem with Allen's original paper, was that it lacked what is called a graceful exit. You need to be able to avoid having your universe carry on expanding exponentially. And it is very easy to show that if your universe is expanding exponentially, you can never form any galaxies, because the expansion is basically stronger than gravity, and nothing ever forms a bound system. And so it is absolutely essential that inflation ends. And that's the challenge, is getting it to stop. It's not starting it. Starting it is, there are lots of different ways of starting it. Stopping it is the trick.
Okay, thank you. Really enjoy that. Thank you.
Is exploding a massive black hole in our universe a good idea in the first place?
No.
No, fair enough. I was just wondering. Tony Morris.
Hi, Sue. Thanks very much for that. Excellent. There's been some work by Roger Penrose suggesting that there's an imprint on the cosmic microwave background radiation that gives us a clue of what happened before the Big Bang.
There have been various such suggestions. The problem is with these things always that there is only one cosmic microwave background. And so it's trying to, what people like Penrose are trying to do is to say that this particular pattern is very improbable. It's very improbable that it occurred by chance, and therefore it must be telling us something meaningful. But it's a bit like looking at this week's lottery winning number and saying, oh, well, there's only a 1 in 14 million chance that number occurred by chance, and therefore it must be telling us something fundamental about the lottery. You need, in order to know if your apparently weird feature is actually meanuful, you'd really want a statistical sample of universes, which we unfortunately don't have.
Okay, can I just go back to the point that Andy raised? So what would be the density of the seed of the inflation compared to, say, the density of a black hole, if that's even a thing we can compare?
They are entirely comparable in the sense that in general relativity, both the beginning of the universe and the black hole both go all the way to a singularity. In other words, they are infinitely dense points. Nobody believes this. The problem is that general relativity is a classical theory. And when you get down to very small distances, classical theories are not appropriate. You should be using quantum theories. And quantum mechanics and general relativity do not play nicely together. And so nobody has so far produced a theory of quantum gravity that is satisfactory. And unfortunately, quantum gravity is what you need to understand both the heart of a black hole and the very early universe. So we can't really say anything about them because we ain't got the tools.
Okay, thanks. Okay.
It's what Donald Rumsfeld would have called a known unknown. We know we can't use what we've got, but we don't know how to make what we've got usable.
Right, okay.
Okay, we're going to take one more question. Andy Devey.
So it's just another question. We've got normal matter, which we are, then that collapses down to white dwarf. Then it collapses again, if it's big enough, down to neutron star. And if there's sufficient mass, it then collapses down to black hole. Has anybody put any thoughts into if there is a stage below black hole, which naturally turns it into a white hole?
Yes, and no. Yes, people have done some work on this. Kip Thorne is the man who springs to mind. You can, and he was doing it to try to produce a credible method of traveling faster than light, so for his mate Carl Sagan's science fiction novel. You can, in principle, produce such a thing, but not with matter as we know it. You require matter with exotic properties, and there is absolutely no evidence for the existence of such. And without that, your wormholes don't stay open.
Thank you.
Okay, Andy. Ladies and gentlemen, I think we have worked so hard enough this evening. Once again, a wonderful talk. Lots of thoughts that have got to go away, sit in a darkened room, think about, and try and resolve. But Sue, thank you very much. And can we give Sue a big Max Swinton Astronomical Society? Thank you. Thank you, Sue.